Welcome everyone in person and online to the Engineering New Zealand Heritage Auckland event. We put together this event several groups, Engineering New Zealand, Auckland Structural Group, and CSOC, and with the help of our sponsors, Naylor Love and Fulton Hogan. We have 3 presentations today, one in person. The title of the presentation is Simple Strengthening and Outline of a Non-Specific Design Approach for Unreinforced Masonry Buildings in Aotearoa, New Zealand, with Hamish, Tocher and Matthew Cutfield. And then we have 2 online presenters, the Historic Wharf Restoration using Modern Materials of Mark Dyer, and Reality Capture and its place in digitally preserving the past of Lennon Bedford. Like Holly said before, we are not taking questions for this event, so we will run the 3 presentations one after the other. I will start by introducing the presenters of the first presentation. Hamish is a design engineer at Holmes Consulting based in Auckland. While he was at engineering school, he ran a heritage society connecting engineering and architecture students and undertaking site visits to retrofit projects on heritage buildings in the Auckland region. Matt Cutfield is a design engineer at Holmes Consulting, also based in Auckland. He undertook a number of design and strengthening projects on masonry buildings, but prior to being a design engineer, Matthew completed a PhD in seismic risk assessment here at the University of Auckland. So with that, I will leave it to them to start.
Ngā mihi kia koutou. I'm Hamish Tocher. Hey, thanks to the in-person audience for coming out tonight. It seems like a big thing to ask people to come to an in-person event this month in particular, so nice to see you here. And to the online audience, welcome as well. This is an updated version of a paper that we gave at the CSOC conference in July last year. So if it looks a little bit familiar at the start, I want to reassure you that there's some new content coming down the line as we get to it. So I'd like to ask you to put yourselves in the mental space for what we're talking about today by imagining that we leave here and we go on a road trip. And let's drive for a little while, and perhaps we get to the point where we're a bit hungry. We want to drop into one of the small towns along the way. Let's go to your favorite small town, whatever that is. You know, the one with the good sausage rolls. We'll go to that one. And so we're going to pull into the main street. And I want you to imagine in your mind's eye what that main street looks like. And I'm imagining that you're seeing something in your mind's eye that looks a little bit like this. So for engineers in the audience, you probably recognize that these are 1- and 2-story unreinforced brick masonry buildings, and that if you've ever worked with those buildings before, they're likely to be earthquake prone. So looking at the street, you see a sort of street of individual buildings, but when we zoom out and we look at the map of that community, we start to see that the issue we're dealing with is a community issue rather than a building by building issue. This is Fielding, and all of those orange dots on the map represent a building that's in the earthquake-prone buildings register and having been assessed as an earthquake-prone building. But it's not just a community like Fielding that's dealing with this issue. We could look at another central North Island town like Levin, or places like Martin, also in the central North Island, or Waipukurau in the Hawke's Bay. And you can see these buildings, these streets look very similar to each other, and that the structures in these streets are similar. It's not just the North Island, it's Waimate in Canterbury, or a town nearer to home like Huntly. And all of these places, the central business district of these communities is constructed of these earthquake-prone buildings. So the way that we manage these buildings in New Zealand under the current settings is through the Earthquake-Prone Buildings Amendment Act, which came in after the Christchurch earthquake. And you can see from the timelines on the screen that the owners of those buildings are facing some challenging deadlines, particularly if they're in the high-risk areas. The latest possible deadline that they might have if they're in a priority building would be 2027. And many of them will be dealing with a time frame that's sooner than that because their building will have been assessed as earthquake-prone before the deadline of January 2020. So from the perspective of owners of those buildings, there's some research that tells us about the kind of challenges that they're facing. So Brent Nakis did some research looking at Waimate, which was one of the communities on the slides earlier, showing that the owners of those buildings might be, that perhaps 50% of those buildings might be demolished under a compulsory strengthening type scheme. and in his later research, reinforcing the idea that stronger regulations around retrofitting are likely to lead to demolition. Looking at the effects on the communities themselves, there's some research which looks at the way that the communities change as a result of the potential demolition or abandonment, with people choosing to leave their buildings rather than to strengthen them. And more recently, some research from an insurance perspective, looking at the major issue being the cost of the strengthening. So most recently of all, an MB survey released last year showing that the distribution of territorial local authorities is uneven about whether or not the strengthening is likely to take place by the deadlines given in the Act. So we think about what the outcomes of these current settings might be for those communities. It's clear that some of those buildings are either not going to get retrofitted by the deadlines, or they're not going to get retrofitted at all. And it's likely to be lower value buildings which are clustered in some of those regional centres. If the owners don't have the ability to repair the buildings, they're also relatively unlikely to have the financial ability to replace those buildings. And so there's likely to be a significant loss of assets in those communities, both kind of cultural and social assets, but also historic heritage that goes along with it. And of course, if inaction on strengthening is one of the consequences of the high cost of the strengthening, it is likely that safety improvements are not being made in those buildings in the interim. So if an earthquake were to happen tomorrow, those buildings wouldn't be any safer than they were in 2011. And to some extent, you can see some of these consequences playing out in small communities like Masterton or in Chicago. So the current process that we have under the Earthquake Prone Building Act requires each individual building to be assessed for its earthquake prone risk. And there's a relatively complicated multi-phase process that goes along with that to assess and design some good solutions for the problems those buildings might be facing. So when we look at what the costs that are associated with that process, and we look at where we're at, as we've said, one of the options is the do nothing option, and it seems likely that this is going to lead to some relatively wide-scale demolition or abandonment of the buildings in those communities. An alternative option might be to look at increased public funding for repairing those buildings, but it seems as though the government appetite for that may be somewhat limited. The Heritage Equip Fund, which was helping some heritage building owners to strengthen their buildings, wasn't funded in the latest budget, so that's not currently an option. So what we're really here to talk about today is whether there's an engineering option to reduce the cost for strengthening those buildings, and can we do that by simplifying the strengthening process that takes place. So the reason why we think there's an opportunity to simplify the strengthening is that the unreinforced masonry buildings in New Zealand were constructed in a very similar way. It doesn't really matter where they are in the country. They tend to share a lot of common characteristics. And there's been quite a lot of research and testing which has identified the likely failure modes that those buildings are going to undergo according to their size and scale and to the specific details with which they were built. There are also some standard details that exist that address a number of those common failure modes. And so an option that we're here to talk about is that we could consider allowing a non-specific design of those retrofits to be applied without a specific engineering assessment to some of those buildings for which this is relevant and applicable. And we're talking about a non-specific design system which is analogous in some way to what we do with timber buildings or what we do with concrete masonry buildings. So it's called, we're talking about it as simple strengthening, and so if it's simple strengthening, it should fit on a slide. So I'm going to try and tell you what we mean in one slide. Bearing in mind that what we're talking about here is some practical and timber-based details that are designed to be installed by people who live in the communities where the buildings are located. So for every building which is eligible for simple strengthening, we envisage baseline measures being carried out. These would be connections between the diaphragms and the walls, whether that's roof or floor diaphragms, the restraint or the removal of chimneys and parapets and ornaments and other things like that, tying together cavity walls with rigid cavity ties. And that's about all for baseline measures. For some buildings, particularly those buildings in higher risk areas, there's a further set of measures that might be carried out, involving the out-of-plane strengthening of the walls and potentially strengthening of some diaphragms of buildings with a plywood overlay. Now, we also want to talk about a situation where most of a given building may be suitable for non-specific detail strengthening, but some elements of that building are not suitable for standard detail strengthening. And we make the case that there could be specific engineering design done to address some of those elements taken out of the context of the building themselves and parcelled out as a small piece of work for a local engineer. So which buildings are we talking about applying this simple strengthening to? Essentially, it's the ones described as typology A to D by the Russell and Ingham paper in 2010. It's 1- and 2-story buildings, either isolated or row buildings, and buildings that meet certain limited geometric criteria. They can't be bigger than a certain height. They need to have a certain aspect ratio, and the hazard factor can't be too large, those kind of things. So we are proposing that buildings can be triaged, therefore, into 3 different categories. Buildings which are evidently okay for simple strengthening, buildings which are evidently not okay for simple strengthening, and they're too complex or too large for this process to work. And also those buildings, as referred to on the previous slide, that can have some specific elements designed by an engineer, but that don't require a full assessment or a full engineering process to be undertaken. So I'm going to pass over at this point to my colleague Matt to talk about some specific details for how we would apply those processes.
So good afternoon, everyone. My name's Matt. So I'm just going to continue on a little bit talking about the simple strengthening idea that we're proposing. And I'm just going to go into a little bit more detail about some of the specifics and how this might kind of play out. Hamish was talking before about baseline measures, and those would be required. Louder, is that right? Yeah, so baseline measures that would be required for all buildings. Those are kind of would be required as a kind of a blanket. So the next type of measure would be a conditional measure, and the first one of those would be out of plane walls. Is probably the most significant conditional measure because it represents one of the most vulnerable modes of masonry buildings, and therefore the most likely to be needed. So the approach that we would use for this would be using timber strongbacks. Nothing particularly new there. They're already very widely used and well understood, but they come with the added benefit of conforming quite well to this idea of simple strengthening in terms of being of timber, so that they're easily available, and the techniques needed to put them together are also relatively simple. Even the connections. There are various options in terms of how you connect the timber strongbacks through into the masonry walls. In terms of, do you do a grouted in through bolt, or you do a Python type screw? I think for us, a Python type screw, a self-tapping screw would be presenting an opportunity in terms of just the simplicity to install. But so the level that we would target in terms of these conditional measures would be the minimum to ensure that we're ensuring that collapse is unlikely in a moderate earthquake, which is conforming generically and generally to the Earthquake Prone Building Act, the intent of the Earthquake Prone Building Act. So just moving on, I think a little bit. This slide it kind of shows what this might look like for a one wide wall of a single story, and you could have this is kind of giving a flavour for this for what these things might look like. This is kind of taking inspiration in terms of a lookup table that would be similar in concept to NZS 3604. I've kind of done a couple of different variants of this for single wide walls on the first story of a one-story building, an upper story of a two-story building, and I also repeated the process for 2 wide walls. So just kind of showing that there are, within this kind of simple strengthening, you can't necessarily always apply a blanket approach. There are some factors that need to be considered, but you can do that in a relatively simple way that's easy to access for local people and without buckets of experience of this type of thing, just using these lookup type tables. So for example, seeing this one wide wall single story, if we were to go to an upper story, the vulnerability increases, and therefore the likelihood of having to install it increases, and the size of the strongbacks increase. Next, if you were to go to a double wide wall, they are inherently more robust, but when they get to a point where that they require strengthening, the loads are higher, and therefore you may end up with some very high walls that are very thick that particularly if they're tall and in a high hazard region, that the timber strongbacks idea becomes a little bit pushed, and they may be, we've marked down there SED, meaning specific engineering design. So the idea would be that those would fit into that, what Hamish was talking about earlier, that we might have to package off a small bit of work and say, right, this part is not quite conforming to our typical details. We need an engineer to have a proper look at that. And the same sort of a process applying to the upper story. So just very briefly, I'm just going to talk about diaphragms as well, which would be the second conditional measure that we'd be looking at. I say here, so the approach that we'd be going for would be a plywood overlay that would be nailed down onto the timber floor. Conceptually speaking, you could do that from below or above, provided that it works well with the connections. And I've said there, affordable and readily available, and I probably potentially could have put affordable in quotes, just because whenever you're talking about diaphragm strengthening, you're potentially, you're much more likely to run into problematic impacts for building owners, because they might, they have bathrooms with tiles and they have walls. And, you don't just have a clean blanket to lay plywood down onto. And so this is the type of thing that if it were possible and suitably safe and in terms of a risk basis to do so, then you would try to not have to do this if you could. So again, so we're targeting the same sort of thresholds in terms of risk, if we go over to the same sort of things, you could have a lookup table that was of the form there. And this is kind of a very simple approach based on the NZSE guidelines. But the pickup here is these two tables are for hazard areas 0.25 to 3, the first one, table number A, and then 0.35 to 4, which is kind of getting up towards Wellington. And even there, it is generally the diaphragms of particularly long diaphragms or that have a strange aspect ratio. And so the high level conclusion is that it's generally written there, I'm just going to quote it, which is generally only atypically long or slender diaphragm arrangements in higher hazard areas that are likely to require any strengthening under the simple strengthening scheme. So we're kind of targeting connecting walls to floors, restraining parapets, those baseline measures, and then for a conditional measure, some buildings will need out of plane wall restraint, and that's and that will be there for a lot of buildings. It's worth briefly noting here that that Hamish and I haven't entirely invented or reinvented this thing out of thin air, and it's not without historical basis. Following the 1989 Loma Prieta earthquake in the San Francisco Bay Area, they had a lot of these, and this is 40 years ago. They had a lot of these same sort of conversations, and they actually did come to an approach where they had two options under the San Francisco Building Code Ordinance 225-92. That one option was you could go with a code-based strengthening, which would be the UCBC in those days, and then they also had a standard detail-based scheme, somewhat similar to what we're talking about, which was called Bolts Plus, and that's been since used relatively widely around some parts of the west coast of the United States. That Bolts Plus scheme included tying together walls and floors, parapet strengthening, and out-of-plane strengthening for URM buildings exceeding where the aspect ratio of those walls was exceeding a given height to thickness ratio. So it's actually rather similar to what we're talking about. That said, and as we're talking about also, there would be eligibility criteria that you would have to fulfill. So this simple strengthening type approach wouldn't be suitable for a large church. It wouldn't be suitable for a big 6-story building in the middle of Wellington, but it would be suitable for a 2-story row of buildings in a small town of an even kind of arrangement. One of the interesting things is that the Bolts Plus scheme required the buildings to have a minimum of 2 lines of lateral load resisting systems. So it was quite strict around open front shops. And I think that's an area that, and we've done a bit further research just looking into that in terms of how, what criteria around this should be, and how risky these things are, and how we can really draw an intelligent basis for what needs strengthening and what doesn't. It's worth just talking a little bit about this simple strengthening concept and how that interfaces with percent NBS, and how that might work from in terms of the existing legislation. And feel free to chime in, Tocher, because he's all over it. Basically, that the percent NBS score is inherently, it's based on a specific assessment of a specific building, and you assess that against using the NZSE assessment framework relative to the seismic hazard of the day. It's entirely building specific, so it's not really suitable or desirable. It doesn't pair up well with this approach. And what we're really suggesting is that in terms of the simple strengthening, I'm just going to put these all up, sorry, that you would calibrate it to a suitable level of risk that is fulfilling the intent of the Earthquake-Prone Building Act in terms of mitigating collapse in a moderate earthquake, but you wouldn't give the building a percentage NBS score. If buildings had simple strengthening and then they then wanted to take it further, they wanted to get to 67% NBS, or they wanted to get up, that there would be nothing stopping them from going further and getting further work done. But this would get it to a benchmark that would then not require them to do any further work under the Earthquake-Prone Building Act. Yeah, so that's kind of how those two were intended to pair together. That said, while we're saying this, we do recognise that this is a kind of a difficult problem in terms of balancing safety risk versus cost on local communities, and there would be a number of issues that would have to be worked through or would be present. One thing is the removal of specific engineering input is always will increase risk of atypical or strange items slipping through that wouldn't normally have done. So that needs to be acknowledged. You would have, the idea with this scheme is that you would have local tradespeople and local councils and so on involved in the construction and consenting of these of the simple strengthening scheme, and then there would be a bit of capability building that would be required to get that online. Another potential problem is that this could be seen as an escape route for earthquake-prone URM buildings that isn't applicable to other types of earthquake-prone building, and that's a fair critique. However, this I think it's pretty defensible on the basis that URM buildings tend to have that nice that are generally quite similar in construction, as Hamish was talking about, relative to a lot of different types of other types of buildings. And then there are also some issues around insurance and liability in terms of if things go wrong, who do you kind of point the finger at? And I think we've got a little bit of guidance on that in the paper and so on. So just in conclusion, there's a bunch of research that Hamish was talking about that from a real estate and an economics perspective, looking at the perspectives of owners of URM buildings, and particularly in small towns, and that research is clearly indicating that they're predicting that a lot of people aren't going to be strengthening their buildings. The cost of the strengthening relative to the value of the building is not amenable to that, so they will demolish or abandon. There will be a lot of that going on. That's widespread demolition and abandonment is a predicted result of the high cost of strengthening, and that is going to pair with potentially some very significant harm to local communities in terms of loss of amenity and heritage as well. One option to help to lessen the impacts of this would be to lessen the burden of this, the cost burden of assessment and strengthening on those building owners by making use of engineering smarts and typical details, somewhat similar to NZS 3604. We've talked about an approach called simple strengthening, which is along those lines. We talked about examples of how engineering requirements might be implemented as part of that scheme, particularly for out-of-plane walls and timber diaphragms. And we talked, just briefly mentioned the Bolts Plus scheme from the San Francisco Bay Area, which is a similar conceptual approach to what we're talking about here. So yeah, so thank you very much.
Thank you, Matt. Next, we have the presentation, Historic Wharf Repair Using Modern Materials. Do you mind, Dr. Ray, introduce yourself briefly before proceeding with the presentation?
Yes, certainly.
Thank you.
Thank you. Good evening, everybody, and welcome. Apologies for the confusion over the presenter. I'll just do a quick introduction of myself, if I can get this slide to slide. My mouse doesn't seem to be working here. Oh, there we go. Yes, so originally I'm from the northwest of England. I studied civil engineering in the Midlands at Loughborough University and researched concrete permeability for my doctorate. I then went into the field of concrete repair, looking at methods and materials before moving over to New Zealand in 1998, where I was fortunate enough to land a job with Sika and got involved with the development of self-compacting concretes. Since then, I've worked in quite a wide range number of different roles prior to taking up the role of civil engineering lecturer at the start of 2020 at the University of Waikato. That was just in advance of COVID, so it was quite an adventure, I'd have to say. Now, at that time, I was introduced to the small East Coast community of Tokomaru Bay, which up to that point I'd not heard of. And yes, so we had a number of undergraduate projects, and they were focused on the local community's efforts to try and preserve and bring the focus onto the historic structures in the area. So the town had a freezing works, has a wharf, and a number of other buildings, including shipping company offices, all of which represent part of the industrial history of the area. So for those of you who don't know, we'll just take a little trip to where Tokomaru Bay is. It's a small coastal settlement at 60 kilometres north of Gisborne. So for those of you familiar with the North Island, just over here on the far east, we'll find Tokomaru Bay. And if we look at the north side there of the bay, then we come across this little finger wharf sticking out there as part of that historic structure. So the previous presenter took us on a little journey around some of our towns. I'm going to take you on a little history trip. So we'll just go back in time a little bit. So the area was established and well settled by Maori for generations. There's plenty of archaeological evidence supporting that. European settlers came and they established farms. And with that, there was a need to improve transport in the area. So they built a small wharf, and this was used for a lot of transport at the time. Vehicular transport, land transport was very poorly developed. So this was the best way of moving stuff around. So the agriculture developed, and with that came the construction of a freezing works at the beginning of the 20th century. So this processed a lot of the local animals for freezing for export. And that was quite a substantial structure, as you can see, for a relatively small place. In 1912, that small wharf, which I showed you earlier, was extended out to reach deeper water. This was so that the larger ships could be loaded and unloaded without having to use lighters to take the goods backwards and forwards. They used wagons drawn by locomotives to get the goods to the end of the wharf in the berthing area. And
sorry, everyone, we seem to have lost Raymond, just some technical issues. We're just working behind the scenes to see how he's going, if he'll reconnect soon.
And Lennon, are you there and happy to perhaps we'll start your presentation, and once Ray gets back on, we can after your presentation he can come on and finish his.
Fantastic. Thank you. So I'm Lennon Bedford and I'm really excited to be here. Sorry I can't be there in person, but I'm excited to have the opportunity to present my paper today remotely from my office here in Christchurch. So I'm going to talk about two of my loves, 3D laser scanning and heritage structures, and how laser scanning can enable more positive outcomes for heritage structures. So with a bit of luck, I can change. There we go. So I'm going to start by discussing the importance of having accurate records of our historic structures, and then move on to how the collection and utilization of laser scanner data can be applied in this space. I'm going to provide some guidance on specifying, commissioning, or even conducting a 3D point cloud survey yourselves, and then look at some local New Zealand case studies to show what is possible in this area. We'll finish up with some key takeaways and a brief look to the future. A quick introduction. So I'm a land surveyor by trade, graduated from Otago back in 2003. Started off as a cadastral surveyor and then had an extended OE over in Switzerland, where I was lucky enough to work for Leica Geosystems, which is a very famous manufacturer of high precision measurement systems, including these 3D laser scanners that I'll be talking about today. And then so I returned to New Zealand with excitement about the latest and greatest tech, and I'm excited to show you how it can be applied in the heritage space, which I have a personal interest in. So why is it important to have accurate records of our historic structures? I'll start with a quote. The importance of systematically examining buildings and standing structures to provide information about the past has been increasingly recognised for providing a platform for improving heritage outcomes. So quality documentation of heritage structures really allows us to assess the value and the evolution of cultural heritage. It promotes interest and involvement in the preservation of our heritage, and it provides for the informed management and maintenance of our important heritage structures. I've used the Aotearoa Lighthouse, which is a short drive from Christchurch, to illustrate how traditional heritage site documentation is put together. So typically sites are documented with written reports, some handheld photography, maybe some hand sketches with hand measurements. And in this case, a not to scale model. And you can see why. It's a challenge with simple measurement techniques such as a tape measure or even a theodolite or total station to capture the intricate detail that is typical in our heritage structures. So to capture the full shape, size, and then context in the surrounding environment, I think there's a better way. What you're seeing here is the result of a 3D laser scan. So how is a point cloud captured? The instrument used to capture the Aotearoa Lighthouse, it's like a RTC laser scanner. It's a tripod mounted static scanner. So you set it up in a position with a good view of your object of interest. You push the go button, it does a 360-degree rotation and captures millions of data points over the surface of every part of the scene within the range of the scanner. As well as capturing a 3D point cloud, the scanner is capable of capturing a high-resolution panoramic image. And this image is able to be overlaid on the point cloud to provide a real color representation of the scene. So here we have 3D point cloud captured by the scanner. Each of these locations, these red dots represents a scan an individual scan. So the scanner is a line of sight technology. It can only measure what it sees. So in order to capture the entire structure, it's necessary to step the scanner around in a logical fashion. These scans can then be joined together into what we see here, which is a unified point cloud. So what you're looking at here was going to be an orbit of the 3D point cloud. So the scanners are capable of capturing very quickly millions of 3D data points, each with an accurate X, Y, Z and coordinate. And together they form the point cloud, which gives us a digital replica of the structure. As well as the point cloud, each of these red points can be jumped into like you would in a Google Street View type interface, and you can inspect the scene with a 360-degree panoramic image. And the main way it's different to Google Maps is that all of this data is millimeter accurate. So we can pick points within the cloud and take point-to-point measurements wherever we have interest. Right, so now you can see the 3D point cloud in all its glory. So the more complex the subject, the more suitable it is for 3D laser scanning. You can see the astonishing level of detail that's possible to capture in literally a couple of hours. I think this took me an hour and a half of work in the field. And then, as I was discussing, we can jump in to the setup locations and inspect the glorious 360-degree panoramic imagery, and essentially visit the site virtually. And this is like a virtual tour, and remove the need for a site visit, which I think is particularly pertinent in this COVID world and moving forward when we're looking to minimize our travel in terms of sustainability. So there's the demonstration of a 3D measurement in space. Right, the eagle-eyed viewers amongst you might have noticed that the roof was missing. So because we were ground-based with the scanner and we didn't have any way of elevating the scanner, the roof was shadowed. We didn't have a line of sight with it. So we complemented the 3D scan by deploying a simple drone and captured simple 2D images with enough overlap to create this 3D reconstruction of the scene. The point cloud from the drone was combined with the scanner, and then this hybrid reality mesh was derived from the combination of the two. And you can see there's no room for misinterpretation of this types of data, like there is, say, with a sketch or a sectional drawing. You can even pick out, the small raindrops sitting on the roof there. So I hope the applications for this technology are rather obvious. It provides a comprehensible archive record of a site or structure, and also the context of it and of its surroundings. I think this is particularly valuable in the case where structures are at risk, maybe due to earthquakes or flooding, other natural disasters, or man-made development. They're preserved in all their glory in 3D digital form forever. They also provide the basis for 3D redesign work in case, say for example, the structural strengthening of a building, or the modification or alteration or extension of an existing heritage site. They allow for the creation of these beautiful reality models, which can be published online or shared in file format, which really can be valuable in increasing the awareness, accessibility, and public engagement with our heritage. And that can be the basis for producing scale models through modern techniques such as 3D printing. How can I utilize a point cloud? Most simply, modern PC hardware and software allows a pretty heavyweight point cloud to be shared relatively easy through the means of a license-free point cloud viewer. So these could either be desktop apps or even a simple web interface through a web viewer. The point cloud can be converted into a photorealistic 3D mesh, as was displayed in the previous slide. The 3D terrain around an object could be extracted, Or we could extract typical CAD type deliverables, such as building information models, which could have asset information associated with it. Or we could even go as far as extracting your traditional 2D drawings, all from the original point cloud. So it's really versatile data. It's important to realize that not all point clouds are created equal. So there's varying hardware available and varying methods and various levels of rigor involved in achieving a positive outcome or a successful outcome. So there's lots of questions, important questions to be asking before you commission or conduct a survey. As I said, the point clouds are not created equal, and there isn't a one size fits all scanner. So, generally speaking, the scanners can be grouped into tripod-based static scanners or mobile scanners, which are either be handheld or backpack mounted or even vehicle mounted. Tripod scanners provide the most detailed, accurate point clouds possible and amazing high resolution HDR imagery. The downside is it takes more time, more planning, more expertise to capture a quality point cloud. And it requires some rigor in post-processing to stitch all of those individual scans together accurately. Mobile laser scanners are fast and simple. You simply push the go button and walk through the scene you want to capture. And there's very little post-processing required because it's a seamless point cloud straight off the instrument. The negatives are the current technology isn't as accurate, as uniform or as dense as the point clouds captured by tripod mounted scanners. They all have their purpose, so it's important to understand what that purpose is before you head out in the field. So the first question you need to be asking is, why is this data needed? Is it simply for a pretty visualization, for conceptual design, master planning and the like? Or is a highly detailed and accurate point cloud required for, say, fabrication of steel members, say, in a strengthening use case? How is this data going to be used? Is the requester of this data or your client, do they have the software that can accept or import a point cloud? Do they have the PC hardware to run it? If not, maybe what they're asking for is a model or a plan or an elevation derived from the point cloud. So a simplification of that dense 3D data. And how are you going to share this data? It can be big. So you could need to consider if you have cloud sharing platforms or physical hard drives suitable for it. But this is becoming less and less of a problem with the development of new tech. Before you begin, it's important to have a detailed list of the objects and structures that wish to be captured. Do we need roof areas? Do we need to deploy complementary capture technologies to capture the scene in detail? Facades, are the ceiling spaces required? So this is possible, but it might require a smaller, more mobile unit. It might require more time. Is the surrounding street and the adjacent buildings, are they important in the scene? It might require a longer range scanner. Are the underground services of interest? So it might involve the deployment of a ground penetrating radar or the like. So it's important to have a good scope in order to be able to budget accurately for the type of survey required. The resolution or the density of the point cloud and the accuracy have a really big or have a significant impact on the cost of a survey. The time involved and the rigor involved in the processing all adds up. It's relatively simple to obtain a point cloud with highly precise, repeatable short distance measurements. So if you want to measure across a room, for example, or through a doorway, that's achievable with simple methods. It's more difficult to create a point cloud with absolute accuracy across a site. So say, if you have a series of 20, 50, 100 scans, then this is where more rigorous processes are required to ensure the absolute accuracy across the site. In terms of density, the rule of thumb is that you should have a density twice as dense as the smallest feature identified in the cloud, and the accuracy of the instrument or the noise should be at least equivalent to this resolution. Otherwise, you won't be able to make out the features you're interested in. Important to know whether or not the point cloud needs to be coordinated in terms of a local coordinate system. This allows the data to be combined with other spatial data sets. And it also, importantly, provides an independent check or verification of the 3D accuracy of the point cloud. But this is a time and a cost associated with it, so it's important to know whether or not it's important for the job at hand. So I'm going to move on to some local New Zealand case studies. First one is the Tug Lyttelton. So first built in Glasgow, operated in Lyttelton Harbour here near Christchurch between 1907 and 1973. And it is still in operation today. They run Sunday afternoon cruises, which my family and I enjoyed. And we read in the paper a few weeks later that it was up on the dry dock for its annual maintenance. So we approached the Preservation Society to see if we could capture it in all its glory with a laser scanner. So this is one of the images captured from the scanner, and you can see the red dots show where the other scan stations were captured. It was about 120 stations to capture the vessel both inside and out. And we captured more than 1 billion data points in the day we were on site. So this is down in the boiler room, and you can imagine it's a really cramped environment. So we chose the scanner which was small enough and mobile enough and quick enough to take lots of scans to transition between all of the bulkheads and galleyways and stairs and things. And this is the result. So this is what you're looking at here is the raw point cloud. And you can see the astonishing level of detail achievable. You can see the guy wires and things all picked up by the scanner. This is an ortho-rectified image of the point cloud. So this simple JPEG image could be shared and is true to scale. So you could take dimensions off this. The point cloud can be sliced and diced to inspect the interior. You can see how we managed to get right down into the bilges, the cabins, right up into the cabin house. Another example of a deliverable derived from a point cloud. So we created a 3D mesh to best represent the surface of the point cloud, and then reversed and engineered a CAD surface from that. And this lightweight CAD surface could be used, for example, to create a 3D print or a scale model of the vessel, or to reverse engineer 2D drawings. To give you an idea of how long this sort of project would take, it took us about a good day in the field, another day to process back in the office, and then another half a day to reverse engineer that CAD surface. The second example is from a customer of ours, Elliot Sinclair, who are based here in Christchurch. And they were tasked to capture the beautiful art centre here in Christchurch inside and out. So sadly, it was badly damaged in the Christchurch earthquakes, but fortunately well insured. So the plan is to convert this part of the art centre into a boutique hotel. And they were tasked to capture a point cloud of the highest accuracy to allow detailed architectural design and structural engineering. And so they chose the top of the line survey grade scanner, and then with a combination of cloud to cloud registration or stitching and target based workflows, they were able to get a point cloud verified down to an accuracy of ±4 millimeters across the whole extent of the site, which I find is really impressive. So they had a control network measured with an independent means, so with a total station and a precise level that they could tie into with compare against the point cloud to put that quality value on it. And it's interesting to see that the time involved in the control survey is similar to the field capture and a really rigorous post-processing routine and QA in order to get the point cloud down to that level of accuracy. And the final use case, the Ning building here in Christchurch. So first built in the early 1900s, a really nice example of the majestic Victorian architecture that was quite popular at the time in Christchurch. Unfortunately, this is the last example left standing of this type of architecture. And unfortunately, it's right in the position where the new multi-use stadium is planned in Christchurch. So it was faced with demolition. Fortunately, the owner was able to negotiate a new spot for this building. So it is going to be cut off at the basement and rolled down the street to the corner a couple of 100 meters down the road. And so Maxim Kovako from Woods and myself donated some of our time to capture the building inside and out using both a laser scanner and again complemented with UAV imagery to reconstruct the roof in 3D digital form. And the results are pretty spectacular. So it's really nice to have captured the building in its original context, in its original location, to be preserved forever. And then this point cloud was taken to the next level. A 3D BIM model was extracted from the point cloud. So these walls and windows and things best approximate the point cloud. And we were able to take a slice through that model and generate a floor plan or a footprint that could be used to design the basement down the road. And then the team at Woods thought this was a great example to show what is possible in terms of 3D modeling. So this is a full, realistic rendered building information model. As you can see in the time taken, very quick to capture, but in this case, this is why I try and highlight the importance of knowing what you're asking for before you start the project. So really labor intensive and expensive to take a point cloud through to a 3D model like that. You would only do that when it's really required. So in conclusion, there's a lot of text on the slide which I don't expect you to read through, but I'd like you to leave with three key takeaways. Basically, I think our heritage structures deserve to be preserved digitally in 3D forever. And the 3D laser scanners is the perfect way to accomplish this. 3D laser scanning can be supplemented and combined with other capture technologies, such as drones or ground penetrating radar, to provide a full picture, both above and below ground. And 3D point clouds shouldn't just address the immediate engineering challenge, but they're versatile enough to meet many ends. So fantastic for engaging the public in the further preservation of these amazing structures. I'll just finish by looking to the future. So there's already been a lot of, the current state of the technology is amazing, but it's only going to get better. There are already flying laser scanners, robot mounted scanners, and the collection of this type of data will only get more automated, as well as the deliverables. So I can see asset management data systems moving fully into the 3D space. I think the capture of these types of captures will become commonplace within the industry. Virtual tours, briefings, health and safety applications will all be possible. The public will be more engaged with their heritage. I could see the digitization of museum pieces, augmented reality representations of streetscapes and heritage features, and even maybe the gamification of our heritage. So I think the future is really exciting. Thanks very much for listening. And if you have any more questions, feel free to get in touch.
Thank you, Lennon. We really appreciate it, and we're glad that we got those videos up and running. We've got Ray back online, and appreciate that we will finish that presentation now. Thank you, Lennon. And over to you, Ray.
Okay. So yes, we got as far as extending the wharf in 1912, just prior to the Second World War, First World War rather. So this was in time for the to meet the UK's demands for frozen produce. So this was carry on anyway. So the local community grew as this as this industry developed. And so by the 1930s, things were looking very good, and they decided to extend or replace part of the timber wharf with a concrete length. So this is a 240 meters of the timber wharf was to be replaced. This was in the late 1930s and built alongside the existing structure so they could continue to use that. And it was a simple trestle structure, series of bents, so driven piles with a cast in situ crossbeam, and then these were connected with longitudinal beams and an in situ slab. And some photographs here taken at the time. So on the left, you can see the new wharf and piles looking landward. And then on the right, the piles close up, and in the background, the piling rig. I guess the left-hand photograph was taken by some brave soul standing atop the piling rig. So this was put together following a fairly simple design and fit for purpose and very good for what it was. So post Second World War, there was a gradual decline in coastal shipping as land transport improved, and with changes in freezing technology as well, the freezing works came to a close in the 1950s. So things started to decline in the area, and the structures were pretty much left to their own devices and started to deteriorate and decline. The wharf and the other structures were given heritage listings in 1984, and there's a category 2 listing for the wharf. But it remained a focal point for the community up until 2017, when it was closed due to safety concerns with deterioration of the wharf structure. So next slide. Okay, this is the community enjoying the recreational opportunities. So it's pretty good at this point just to think a bit about what the heritage means. So it's a pretty broad concept. So for this location, it's primarily focused on the history, the links to that history. So the industrial heritage of the 20th century. But it does relate to a range of different physical factors, technology and engineering, the historic value, culture, and community identity. So it's very easy to just consider the wharf as a historic icon, but it is more than that because it's significant within the local culture. And it's worth noting that in addition to Tokomaru Bay, there's another bay, Tocher Bay, further down, which has a more famous wharf. But these two wharfs are the only two of their type actually listed as heritage items. Tocher Bay Wharf has been extensively renovated, so it could be said that it's lost some of that original authenticity. So this means that Tokomaru Bay Wharf is actually, in its virtually untouched condition, pretty much one of a kind. And the importance of these structures is going to continue to grow as they become fewer and fewer. So this is one of the things that's driven the local community to focus and highlight this history. And they formed a heritage trust in 2015. And you know, it's probably worth saying that while all this is going on, the structure itself, the wharf structure, is prone to the ravages of time and tide. In a marine environment, concrete deteriorates. The reinforcement is attacked by chlorides. We get staining, cracking, spalling. And in the case of the wharf, this is no different to many other structures of this era. When it was built, the concepts were unknown, so nothing could be done or nothing was done to address the risks. So we can see the issue clearly represented in the piles in this photograph here. So you can see that in the splash zone, the concrete has spalled off, leaving the reinforcement exposed, and in many cases, actually the reinforcement is missing or broken. And virtually all the piles are in this condition. You can also see in this photograph some of the beams for the structure are also exhibiting spalling. So it's things are looking a little bit grey, not so bright for the long-term prospects for the wharf. So this has prompted the local community to put in some effort to try and make some changes to improve things. I'll just talk briefly about repair here. So for conventional concrete repair, it's well documented. We take out the deteriorated materials, we replace them, and where necessary, we provide some additional protection. When we're carrying out repairs for historic structures, the same process has applied, but we need to do it in a much more sympathetic manner. We don't want to completely replace a historic structure with a new structure made of different materials and possibly even in a different form. So what we need to do is to achieve adequate performance, but with the lowest level of intervention. So we don't want to completely replace everything. We want to try and retain as much of the original as we can in terms of behavior, in terms of appearance, and so on. So in terms of the wharf, the investigation into the actual structure concluded that it needed attention, especially to the piles. The proposal was for replacement or repair. And the repair option was to adopt something similar to a Tokomaru Bay wharf, where new reinforcement was put in place, and then the piles had a concrete jacket cast around them. So the Heritage Trust in Tokomaru Bay, they raised some funds and they commissioned a proposal for trial repairs. This was based on that model, and these were scheduled for the summer of 2020 and 2021. So again, with a local community raising funds, trying to get the sort of money they needed to engage a contractor to carry out the work was beyond their means. So they wanted to set out and find methods or materials which would enable them to actually undertake some of this work themselves, certainly for the trials, because they felt that once the trials were proven, then they would get more funding. So they needed simple options. And so they did some pretty good background research all by themselves. One of the options they came up with was the use of glass fiber reinforced polymer rebars. So this has the benefit of being corrosion resistant, so it removes that need for additional protection in the future. It's a lighter material, which means that in terms of the equipment needed and the people needed, it's easier to get it into place. Also, because of the way it's made, any shapes have to be formed at the time of manufacture. So this removes the need for on-site bending and fixing. So all they have to do is make up a lightweight cage from preformed components and a packet of plastic zip ties. So that's something they could do themselves. And another added benefit of this material, it was locally made at a company in Gisborne, and they supplied the reinforcement. And that's a stack of the pre-made cages. They made half the cage, so it could be fitted around the piles for the repairs and then tied together once it was in place. But these are pretty light. Now, the other big problem they had, or big challenge, was the actual concreting material, the repair material. So with conventional material, concrete, you've got to compact it, you've got to place it, and you've got to do all of this under a wharf in a confined space, exposed to tides. So it's really quite a challenging environment, even with a professional experienced contractor. Sprayed concrete was used on some of the Tokomaru Bay piles, but this really requires too much specialist equipment, specialist operators, And in our modern environmentally conscious days, it just wasn't a practical option. But they did their work, and they identified self-compacting concrete as a possible solution, because this can easily flow into those spaces, doesn't need to be compacted separately, so it has the potential to meet their needs. So they could pour the concrete off the wharf or from the wharf into formwork around the pile, and it would do the rest of the work itself. Now, fortunately, with my prior experience, we were able to do some design work at the University of Waikato. We came up with a mixed design, which they were able to trial. So they made up a mock-up of a pile with formwork, reinforcement, and they poured the concrete, and that was the result. So they were very satisfied with the result. The photograph at the top left is the flow of the concrete. That's a flow spread test that we use for self-compacting concrete. So this is a very positive outcome. And on the basis of that, they proceeded to do some of the trial repairs. So they did the preparation. This, in fact, is our research student posing for a photograph, pretending to work, I believe. So prepared the concrete, took out the damaged concrete, cut it back to a sound surface, removed the reinforcement, put in the new reinforcement, tied that all together, put in the formwork as well. And then with a very simple system, length of pipe connected to the bottom of the formwork, a tractor mounted mixer, which they purchased themselves, and a couple of locals to load the mixer. They were able to pour the concrete and following day strip it down, and the result was 2 successful pile repairs at the beginning of last year. This is taken a few weeks back, this picture. You can see some of the other piles in the background there which still need work. So this has generated a lot more interest for the community. There's promise of more funding, but it's also added to the heritage value. So it's added to the history. The community used to be part of that history in terms of the freezing works and the activities there, but now it's evolving. So this is a new chapter. So they're now part of that saving the wharf. So they haven't just raised funds. They've investigated the requirements, they've determined what to do, and then they've actually gone and done it. So yeah, in terms of heritage, it's adding to that culture, that cultural meaning in terms of the community engagement, and it's certainly helping to engage the community more with the project. I suppose on a sobering note, there's a lot of historic structures in this area. This is the inside of the freezing works. And a lot of it, unfortunately, will eventually be lost. You know, the community can only do so much. But yeah, the stories will remain. As long as there's some remnants of the structures, there'll be significance there. But this added chapter now, this adds to the story. There's a new evolution of what's happening there. So the future's in the hands of the community here, and I guess you could say a few of our fresh-faced Waikato undergraduates. We've got ongoing research because we want to see if we can restore the piles to the original profile without the concrete jacket. And this, I think, will not only save the structure, but it will retain its authenticity as well, and be just as easy to achieve, hopefully. And so that's things are looking a little bit brighter. Yeah, this is a nice blue day, and just to acknowledge, I think the university has provided support and assistance and some student sponsorship for this. The Tokomaru Bay Heritage Trust, obviously, for their hard work and support, and also a special thanks to the Tokomaru Bay Virtual Museum who gave permission for the use of the historic photographs for this presentation. So thank you for your time, and I hope you enjoy that. And I'll hand back now.
Thank you. Thank you to all the presenters.
Thank you, everyone. everyone for joining. Apologies for the technical issues we did face. Got there in the end, which is great. We hope you enjoyed tonight. Thank you and have a good rest of your night.
Hey, thank you. Goodbye.